Previous exposition, I talked about the orbit, and before that, talked about the differential equation, and before that one, talked about the group. And in my group video, I talked about non-commutativity or non-transitivity between two matrices or two elements in a group. So I discussed or I mentioned a group of matrices or the group of all matrices, and I told you guys that any two matrices cannot be interchanged when we compose them. So when we sort of multiply two matrices, they are not. It's not. We can't switch them around when we do that. So A B C D E F G H is not equal to E F G H times A B C D, and we read from right to left. So it's not the same, and it's easy to show this by actually just multiplying them and composing them. And so today we're going to be talking about matrices. What exactly is this rectangular array of numbers? Why do they look like that? Why are they like this? So before I start the lecture, I assume that you guys already have at least a small understanding, or at least you guys already know what Euclidean space is. So Rn. But we're gonna be using the subspace R2. So two-dimensional Euclidean space for most of our examples about matrices. So what are matrices? Matrices is a matrix. Well, matrices is plural for a matrix, and a matrix is a rectangular array of numbers. There. They're just basically a rectangular array. This is a 2 by 2 matrix. And the n by n matrix is a square matrix wherein n is any number. So this is a 2 by 2 matrix. And you guys keep talking all the craze about matrix. Whenever I say matrix, you guys probably think about the movie or something like that. But when in mathematics, when we say matrix, it's a rectangular array of numbers. Well, this one over here is a square matrix. A square matrix is basically a matrix that has the same number of rows and columns. So this is this going down like this. This is the first column, and this is the second column going like this. And rows goes like this. So this is the first row, and this is the second row. And these rows and columns are mostly denoted by ij. So if we want to call on or specify or want to codify the sort of coordinates of each element, we sort of just say a to the ij, where I is the row of the element and I is the column of the element and j is the row of the element. So if we want to say, or if we want to codify or specify or denote d in this sense, we say a 2 here and then 2 down here. So it's 2 or 22. I is 2, j is 2. So it goes 2 here and then down here. So it's 2. So it goes down. Instead of going up like how normal coordinate system coordinates go, or Euclidean space coordinates go, we go down here. So we go down. So it goes here and then go. So it goes left to right. We read I and j left to right and then up to down. So this is a 2 by 2 matrix. But really, matrices can be any dimensions, really. And dimensions basically just what are the n's here? What's the n? Well, most three-dimensional examples uses a 3 by 3 matrix, A, B, C, D, E, F, G, H, I. And there are many types of matrices. The most common one, which is used in engineering and quantum mechanics, is the Hermitian matrix, which is a matrix whose conjugate, who has a complex conjugate and is complex. So a conjugate is just the opposite. So if we have a positive sign, its conjugate is the negative version, and vice versa. And it contains complex numbers. That's what a Hermitian matrix is, but that's another topic for another video. And so what matrices do, what we mathematicians think when we see a matrix is transformation. So the reason why I was asking you guys I was requiring you guys to have at least a small understanding of what Euclidean space is because that's what we're going to use to visualize what these guys do or what they sort of represent. So the first thing that I'm going to tell you guys is matrices are linear transformations. And you guys already know transformations. It's basically a function that takes any vector and spits out another vector. So a matrix, here's the first fact, matrix is a linear transformation. That's the first fact, fact 1. Fact 2 is that matrices tell us the new basis of the system. So before I discuss what linear transformations is and what matrices exactly tell us, first I need to discuss with you guys what a basis vector is. Now you guys know what a vector is. I discussed it in my linear algebra extras episode, my Femboy Mathematics channel. It's an arrow in space. Well, we can think of it as an arrow in space. We can think of it as a rectangular array of numbers, like this, or a row vector, AP. You can think of it like that. Or a column vector. This is a column vector, this is a row vector. Or we can think of it as an element of a vector space, V. Well, that's sort of new to you guys. A vector space is just a set with vectors. So it's a set that has vectors wherein the vectors can be added, subtracted, multiplied, divided. You name it. It's there. That's a vector space. And we can think of it as it's sort of a manifestation of something larger, or it's a small part of something larger. You can think of that. We can think of vectors that way. So basis vectors are basically what tells us what our coordinate system looks like. So it's in the name, it's a basis vector. So it's the most basic vector you get, and which is why basis vectors, I hat and j hat, has a unit measurement or a measurement of 1 in its, or their norm is 1. Norm is basically just the length of the vector. So yeah, its norm is denoted by these two sort of absolute value things. And say we have a vector v. The norm basically just tells us the length of the vector v. And so what exactly are I hat and j hat? So I hat and j hat, as I said, are the basis vectors of a system. So we're not usually using the Euclidean space in the traditional sense, but rather we are sort of using it as a sort of visualization for what our system looks like. So this is R2. We can think of it as R2, or it's a vector space that has a dimension of 2, right? So this, let's say this is 1 minus 1 on the y-axis, 1 minus 1 in the x-axis. This is x, this is y. The measurement, or actually the coordinates for I hat and j hat, this is I hat, and this is j hat. This is j hat. J hat, I hat. And we can think of this as, well, we can sort of write it down. I is 1 in the x direction, so that's 1, 0. And j hat, it goes up, so but it doesn't move in the x direction. So j hat is 0, 1. And yeah, that's what they are. They tell us exactly what the grids look like, the spacing between the grids, what they look like. And if we change the basis vectors, we essentially change the entire system. So this basically tells us how far this is, what 1 cube is like, what the area of 1 cube is. So let's say this is 1, like how you see on the map, like the grid. We can think of the coordinate system as a grid, and this tells us what the grid should look like, and the spacing between each space on the grid. And sorry, there's talking in the background, it's my relatives. So anyway, yeah, where was I? Right here on the spacing. So it tells us the spacing and what the basic form of the coordinate system, what it looks like. And so what matrices do is they change this stuff. They let us tweak the basis vectors so we get what we want, the ideal coordinate system. So fact one, a matrix is a linear transformation. So what is a linear transformation? It's a it's a function that takes any vector and then spits out another vector. Well, v1, let's say v1. So put a vector inside this function and then it gives us another thing. And so a matrix, well, let's say A is that. It's essentially a linear transform. And when a linear transform is applied on a system, yeah, the J and I is J hat and I hat are changed. But the spacing between any coordinates or any lines on the grid that we construct is evenly spaced, and none of them is really bended. So if this is not, if the matrix really bends the lines, it's not really a linear transform, it's something else entirely. So yeah, lines stay evenly spaced and all that good stuff. So, and it changes J hat and I hat. So the way we sort of encode this change of basis vectors is through the rectangular array that I said a while ago. A, B, C, D. So in the 2x2 case, this part over here tells us where I hat goes to, and this part over here tells us where J hat goes to. And if you'll notice, in your algebra class, or linear algebra class, when we multiply a vector and a matrix, it's usually like this. So we have a matrix A, B, C, D, and we have a vector X and Y. That becomes, well, that becomes a new vector, AX plus BY, and then CX plus DY, where dy is not a differential of y. So it's just a multiplication between two numbers. So a, b, c, d, x, y, all part of the integers. I'll restrict it to the integers. So it's simpler. So we don't have any rational numbers. So z. Oh, I actually want to write that more fancily. Let's write z how I practice that. I practiced writing Blackboard bold z here a while yesterday. There, Z, fancy Z. It's a good way to show off to your classmates whenever you're actually talking about linear algebra in class. So anyway, yeah, I'm gonna restrict those to the integers so that our work is simpler. So yeah, as you can notice, it's sort of like this, and we can split it up into AX, CX plus the vector BY, DY. So we sort of apply it on each of those stuff, and we can actually sort of formalize the definition of a vector as this. Alright, say we have a vector AB. We can split it up into AB times I hat plus AB, oh no, that's B, that's just B, AB times J hat. So we can sort of do that instead. We can show it like this instead, and it's gonna be the same thing anyway, because I hat is just 1 0, and when we multiply that we get a 0, and this is just gives us 0b. So and then add that we get ab, so it's the same thing. So I'll show it here. AB times I hat, and I hat we know to be 0 1 plus AB times J hat, which is just 0 1, and that's just b times 0 is 0, a times 1 is a, that's a 0, plus a times 0 is 0, b times 1 is b. And then just add these two vectors together. We get ab. Exactly what's over here. So yeah, it makes sense. So when this is actually what I'm talking about. This is the L of vector v that I was talking about a while ago. We apply this onto this. So we multiply this onto this. We apply this function on this vector. And when we apply this to all elements of a vector space, we essentially get a change of basis. And so that's really what the matrix does. This is what this thing does. So I'm gonna write one example here, or draw one example here. So we have I hat and j hat, and we all have evenly spaced lines. Let's say this one's over here. It's not crooked. So, and then it's evenly spaced. This is just a rough example, so like take anything. So once, let's say this is 1 1, this is 2 2 over here. All right, let's say I want to move I hat and j hat. Let's apply this one over here. Let's apply the transform. Let's say I want to move this over here and move this over here. So I want to move I hat to 1 1 and then j hat to 1 minus 1. Yeah, 1 minus 1. Let's do this matrix. So first things first is that we move this vector, the tip of this vector, to 1 1. So we move it over there. It's over there now. And let's move this to 1 minus 1. And then so from there, sort of use this as a reference, and then sort of just draw an entirely different coordinate system. So I'm gonna draw the new xy axis. So this sort of tells us the new xy axis, and then I'm gonna do this over here. So right there, perpendicular. These two lines are always perpendicular to each other, and then sort of from there we can just draw the lines. It's evenly spaced. Don't worry. Just remember to keep it evenly spaced. I know it's not evenly spaced for me, but just take my word for it. It's evenly spaced, well, supposedly. The computers does it better. I wish I could use Manim to do that. So this is our old thingy, and then this tilted version is now our new one. It's basically just a rotation. We just rotated every vector this way. So what does it changes the coordinate system itself. So this matrix alone, it changes the entire coordinate system. But if we apply it on the vector xy, let's say we have a vector, well, right here. Let's say we have this vector over here. This vector 0 2. It moves it onto this part over here. It moves it onto here. It moves this vector onto here. That's what it does. That's what this times xy is. We're in xy is just 0 2. That's what it does. And so that's basically the gist of what matrices are and what they do to a coordinate system. They let us tweak the initial coordinate system to however we like, so that we get to play around with it, and then not really play around with it, but work with it. And they basically are a type of function. And yeah, there also are things called inverses. It's basically just doing the opposite. So the inverse of this is just doing it the other way around. Sorry, I had to stop the bubble. So that's what matrices are.